we thought we would present kind of the roadmap for GeoDa and the future of GeoDa, which is really what Jeune has been working on. And initially, I was going to give a brief introduction and kind of setting the context for this, but then next thing I know is Julia has me scheduled to do a full presentation. So what I want to talk about today is really two things. One is a paper that Jeune and I just got accepted in geographical analysis on Toblers Law in a multivariate world. And really what that's about is ways of thinking about spatial autocorrelation when there's more than one variable involved. And that's actually not that simple. So part of what I'll talk about is some things that came out last year, multivariate local Geary, local joint counts, and quantile ISA, which are all related. And then also about some brand new stuff that really connects notions of distance in attribute space with distance in geographical space. So I think Julia sent the latest copy of the paper. It's been incredible fast turnaround because I think I submitted it around February 6th, so it's already accepted. And what I want to do first is give a little bit of kind of context about Toblers Law. So this paper is, or this article I should say, is coming out in a special issue in memory of Waldo Tobler, who passed away, I believe, 2 years ago. And it's really interesting. I had met him. Well, I know him very well. He was a colleague of mine at Santa Barbara, but I hadn't seen him for several years, and I saw him at the Western Regional Science in Pasadena, where I introduced Marinia to him. And next thing you know is that he's emailed to Marinia about sending her stuff about migration, and then he had a heart attack the next week. So I'll talk a little bit about Toblers Law, and then really what I want to talk about is this difficulty of dealing with spatial autocorrelation in a multivariate context, and give a little bit of background, and then give the three main parts of our little paper where we push Toblers Law or think about Toblers Law in multivariable context, globally, locally, and then regionally. And then depending on how much time I have, I'll show how some of these things work in GeoDa. So many people have actually not seen this article. Everybody cites it, but it's kind of an obscure thing actually, came out in 1970. And it's nothing to do with laws of geography or anything like that. It has to do with how to simulate population growth, specifically in Detroit. Waldo, as you can see, used to be at the University of Michigan before he went to Santa Barbara. So basically what Tobler is saying is, one way we could model this is by relating the population in each cell to what's going on in all the other cells. And then he says, instead of using this approach, I invoke the first law of geography. Everything is related to everything else, but near things are more related than distant things. That's the famous first law of geography. And just to kind of tongue-in-cheek show you the result of his simulation, that's the map at the bottom, which shows population growth in Detroit. Now, if you know anything about Detroit, Detroit's population in 2000 was about a third of what it was in 1950. So there was no growth. It was all decline. But of course, his model was not set up to capture those major structural changes in the automobile industry. And then there's another less commonly cited paper of Tobler, which is also relevant in the context of the talk here. It's called A Cappadocian Speculation, and it came out in Nature. And basically what it is, oh, my my headphones are talking to me. The Basically what this is looking at old tablets and common mentions of certain cities, and from that, deciding where they might be geographically. So this is a form of multidimensional scaling, as we'll see later. So there is a measure of similarity, and from that come these locations in two-dimensional space. Okay, the first law, what's the context? As I mentioned, it was a model for population change as a function of only the values in nearby locations. So that makes it a local operator, and it's also important to realize that the context was very much single variable, univariate. Right. Yeah. So as I mentioned, is widely cited. In 2004, the Annals of the AHG spent a special section on Toblers Law, where many people commented on it, and basically the comments were along the lines of, laws are irrelevant, or Tobler is wrong, there's directional effects, there's heterogeneity, all these kinds of things. And in his classic fashion, if you knew him, Tobler's rebuttal was the fact that near things are more related than distant things seems a fundamental property of geography and rather easily explained. That's it. Okay, but then he also points out that the statistician Ronald Fisher in the early 20th century also mentioned that the widely verified fact that patches in close proximity are commonly more alike as judged by the yield of crops than those which are further apart. So that's the same thing. And some people might suggest that Tobler knew about this, because one thing that Tobler was really amazing at, anytime somebody would give a talk in Santa Barbara, he would say, oh, so-and-so in 1892 already did this, or something along those lines. So I wouldn't be surprised that Waldo actually knew about this Fisher quote. So what is this law really about? It's about two concepts, and they're very similar concepts, but also very different. It's a concept of near and related. And near, of course, is geographical similarity, and related is attribute similarity. And everything in spatial autocorrelation, spatial interpolation, local spatial analysis is about the tension between these two. And in a univariate context, it's fairly straightforward. You look at a variable in a location and compare it to the values close by for the neighbors or with a given distance band. So that's pretty straightforward. But when you go to multiple variables, it's not that straightforward, because you have to think about, what does this really mean? Near in geographical space doesn't change. And there's been generalizations where you use network space instead of physical distance, but that's all basically the same thing. What is more difficult is what is related in multivariate setup. And the way I like to think about this is as a measure of distance in multi-attribute space. And the reason I like to think of it that way is that it's very intuitive, as I hope I'll be able to show. And it avoids a lot of problems that you have with cross-product statistics like Moran's I and similar. So basically what I'm trying to find out is a way to quantify that nearness in geographical space matches nearness in multi-attribute space, or in other words, that geographic neighbors are also attribute neighbors. Okay, multivariate spatial autocorrelation. Multivariate is difficult business, and people don't always realize that, because we tend to think in 2 dimensions, possibly 3, but it's quite different when you move to higher and much higher dimensions. The geometries involved are actually very strange, and I found them incredibly intriguing. And this notion of the curse of dimensionality was formulated a long time ago. Basically, it means that techniques or concepts that work well in small dimensions either break down or become way too complicated or computationally infeasible in higher dimension. And just to illustrate that, I'm using the original example of Bellman, basically paraphrased a little bit. So basically the idea is, if you're going to optimize a function, one brute force way to do that is to take an interval and divvy it up in equal parts and just evaluate the function for each of these values, and then pick the highest one, and then maybe cut the interval in a smaller part and do the same thing again. So just for the sake of the argument, think of this as a problem where you take one dimension and divvy it up in equally valued evaluation points. Well, it turns out, it's pretty straightforward, that the number of such points grows, of course, with the dimensions in a power way. So for k dimensions, you need 10 to the k evaluation points. For 10 dimensions, that's 10 billion points. And just to show you how quickly this gets complicated, so we start in one dimension, we have 10 points. 2 dimensions, we have 100 points. That still seems very reasonable. 3 dimensions, all of a sudden we have 1,000 points. So as the number of dimensions grow, this is not a feasible way to deal with it. There's another aspect to high dimensions that is less familiar, and that's the so-called empty space problem. In that higher dimensional data spaces are exceedingly sparse, lots of empty space. It takes a long distance to go to the nearest neighbors, and there's some really weird things where basically mathematicians, topology people have figured out that some data distributions become concentrated in the core of the high dimensional space, and then there's spikes to the outside, very weird stuff. So just to make this concrete, here I have 10 points with 3 dimensions. So if you look at each dimension individually, these points seem fairly close together. They're just random on a 0 to 1 scale. But then if you put them in a 3D space, they actually are floating very far from each other. And so you could just imagine what happens to 10 points in a 6-dimensional space. They're incredibly far from each other. So this means that in order to do meaningful high-dimensional analysis, you need a lot of data points, because otherwise there's just mostly empty space in these high dimensions. So starting to think about that, what is really multivariate spatial autocorrelation about? And I feel that in the older literature, this got a little bit confused with regular correlation because of the cross-product nature of Moran's I, which is like a correlation coefficient. So as long as you have one variable, autocorrelation is very clear what it is. But if you have multiple variables, what is the auto part? Because they're also intercorrelated themselves in place. So that's where things get very tricky. And so one way to think about this is that it's really not about cross products or internal correlations, but it's really about what is called a tuple of values for different variables and comparing the whole tuple into different locations. And so then the question arises, how do you quantify the similarity between these points? And the way I like to think about this is just by using distance. So in the earlier literature that I was referring to, it's a little, it's difficult and it's a little bit artificial in that it just doesn't work. It's very difficult to tell apart what is due to the spatial effect versus what is due to simple correlation. You know, if you look at crime and employment, they're related, or crime and unemployment, they're related. So you look at crime in one place and unemployment for the neighbors, they will be related, but are they related because crime and unemployment are related, or are they related because they're neighbors? And that is the tricky part that some of these approaches try to deal with, either by moving to principal components, and there's a classic article by Wartenberg in '85, and then was kind of rediscovered in the early 2000s, and a number of people refined it. And then there's a couple of papers by Lee where the Pearson correlation and the spatial correlation are separated, but it makes some fairly strong assumptions about the strength of the correlation. So I looked into this, and actually we started working on this some time ago. Levi Wolf also worked on this a little bit in terms of the Moran-Xi part, but then I really got dissatisfied and decided the way I like to think about it is just think about it as distances. So we define a distance in attribute space, which is a standard machine learning technique to characterize similarity. And we asked the question, how does this distance measure relate to geographic distance? So is close in geographic space also close in attribute space? And this theme will come back, over and over in different guises. That's really what I've been interested in the last couple of years, is how can we think about this in more than just a mechanical test, like the multivariate local Geary is just a number, and then, it's fairly mechanical and arguably fairly difficult to interpret. But then Jun and I worked on a local joint count, which is easily extensible to multivariate setting, as long as there aren't too many variables, because it is 0, 1, you very quickly run into situations where there's very little overlap between the ones, so then it doesn't work anymore. And then a slight variant of this is the multivariate quantile ISA, which is essentially turning a specific value range into a 0, 1 variable and then applying the local joint counts to it. So there's really nothing different in the multivariate quantile ISA. It's just I think, actually a very useful interpretation or application, if you wish, of the idea behind the local joint counts. So these papers all came out last year, even though they were written at very different points in time. So the multi-Geary, the joint count, and the quantile local spatial autocorrelation. And if you're not familiar with, just to refresh your memory or introduce the concept. So distance, Euclidean distance in 2 dimensions, very straightforward. And then if you think about the local Geary, it's really an averaging of the distance between a location and its immediate neighbors. And because of the nice additive form of these square distances, it's very easy to extend this to multiple variables and show that a concept of a multivariable Geary, local Geary, is simply the sum of the univariate local Geary. So that's all very straightforward. Where it gets difficult is in assessing significance, and I'll show you during the demo some issues that we run into. So I still like it, but I've cooled a lot on it because it's sometimes, I don't have any problems with this. Basically, what I do is a lot of sensitivity analysis to see when groupings pop up and when they disappear, but a standard statistician would say, well, where's the p-value, and how do you know that this is significant versus the other one? And in essence, you don't, because there's way too many multiple comparisons going on. So the local joint count is very simple, basically Moran-like statistic, but is a product of zeros and ones. And there's a difference between cases when the 2 variables can happen together in the same place and versus when they cannot. So, when you have a particular land use, for example, then it's one land use or the other. It can't be both. But if you have, say, a land use and a type of building, then you can have both. And then you can see whether these coincidences of two types of events also occur among the neighbors, and that's what the local joint count statistic is about. And it's readily extensible to multiple variable co-location. But as I mentioned before, you can't have too many variables because very quickly there is not enough overlap, so you don't get meaningful co-location, so to speak. Okay, Toblers Law, back to Toblers Law. And so basically we're thinking about, okay, this near and related, how can we push this into visualizations or ways of thinking about this when multiple variables are present. And in the paper, we outline 3 different ways of approaching this. One is a global way, focusing on distance decay in the 2 dimensions. The other one is a local one where we have a new local neighbor match test, which turns out to be incredibly simple. And then the last one is more about enabling the visualization or thinking about the tension between attribute similarity and spatial similarity when we're trying to build clusters, which is a slightly different thing. So the data, I know Julia doesn't like this data set, but it's because it's small. I like it because it's small. So it's easy to use in demonstrations and you can actually see what's going on. I was debating whether to use this one or Marigny's, 700 or something census tracts for Chicago, but this is a little easier. You have to know less about the data to actually see what's going on. So as it turns out, this is a historical data set by André Michel Guéry and was one of the first multivariate statistical analysis in 1833 that also used maps and geographic visualization. It's an R package. It's now also a GeoDa sample data set. It's been used by several people as illustration of multivariate situations, principal components, things of that nature. They're basically, all these replications use the same 6 variables, 2 crime variables, literacy, donations, illegitimate births, and suicides. The strange thing about these variables is that they're the reverse of what they usually are. So a crime rate is not crimes per people, but is people per crime, so that the larger number is always better. So that's, a little unusual, but once you know it, it's the same. Now, as it turns out, and I didn't realize this till I started actually digging into this data, this is a terrible data set to look at multivariate things like principal components, because as you can see, the correlations between these variables are very low. And principal components is all about reducing large numbers of variables, large dimensions, to manageable smaller dimensions because you exploit the intercorrelation that is there between the variables. And actually, when you run principal components on this data set, one criterion of picking your components says you should pick 5 components. So to go from 6 dimensions to 5 dimensions is not exactly dimension reduction. So this is a really bad data set, but nevertheless, I will persist. It's even bad geographically. These are the box maps of the 6 variables. And if you just look very quickly, you see that some of the blues are in the south, other of the blues are in the north, and same with the other colors. So if you overlay these on top of each other, there is very little overlap. There's very little match. So this is not a situation where, say, in machine learning, often you have co-location, looking for co-location. So you say you turn each of these variables into their quintile or something similar, and you find observations that are in matching quintile. Well, there are almost none in this data set for these 6 variables. And this is another reflection of the fact that the correlation is so low. So that's, they're both part of the same thing. Okay. I'll go very quickly and then I'll take a little more time when I do the demo. So the first idea is, okay, we have distance in geographic space and we have distance in multivariate space. So why don't we compare the two to each other? And this is actually not a new idea. There's some work in the 1990s that looked at basically correlation and rank correlation between different distance matrices. So this is in biology, where distances were computed based on genetic characteristics and things like that. So the idea was really to find out whether different distance matrices captured the same kind of general pattern among the data. And so rather than doing the correlation, which we do in the paper, we thought it would be nice to visualize this and simply have a scatter plot. Now, this is a scatter plot of distances, so there's lots and lots of points. So rather than showing all the points, we just show a smoothing. This is similar to a multivariable semi-variogram, but it's a little bit different in that it doesn't look at the expected square differences, but it just computes a distance, Euclidean distance in the dimensional, in the attribute space, and then plots that against the geographical distance. So this is for each variable by itself, and by and large, we see things that we would expect, namely that there's very little dissimilarity with very small distances. Then it goes up very quickly and then kind of flattens out. For some, it flattens out more than for others. We even have a pattern where it comes back down, which points to potential, regional effects that I didn't even, this is just for the illustration of the concept. But then this is very easily, so you would say, why do this instead of a variogram? And honestly, there is no good reason. It's the same. But once you go to multiple variables, it's a lot easier to do the distance. And here's the brown one is for 3 variables that I'll be using in the demo. And the reason for that is that you can actually see them in a 3D scatter plot before you jump into the higher dimensions and you can't see anything anymore. So one thing that this illustrates is that, as you see, the blue curve is for the 6 variables, that these are much further apart in attribute space than the 3 variables. So this is the empty space phenomenon. But for both of them, at least in this particular example, it seems that Toblers Law generally, quote unquote, applies, and that there is a stronger correlation close by, and as the distance increases, it flattens out and locations become essentially uncorrelated with each other. So that's the global perspective. The local one is the one I like the most. So this actually came out of my lectures, my classes, where I started thinking about how could one visualize this tension between similarity in attribute space and similarity in geographic space. And so this local neighbor match test essentially takes 2 weights matrices based on nearest neighbors. One is the traditional, k nearest neighbors in geography. The other one is k nearest neighbors in the multi-attribute space. So we do say k equals 6. We have the 6 nearest neighbors in geography, 6 nearest neighbors in attribute space. And then the question is, how does this match? How many of these geographical neighbors are also attribute neighbors and vice versa? So we call that a neighbor cardinality map. And so it's also possible to find the probability of how many shared neighbors there are. It's simple. It's not that simple, but it's straightforward combinatorial stuff. So you can actually get a p-value. Again, these p-values, I would take them with a grain of salt because there's so many multiple comparisons going on and other things that affect what the true type 1 error would be. But it's a quick and easy way to see, well, how rare is this? Now, one thing to keep in mind here, and this is something that also happens when you use the local joint count statistic, is that K, the number of nearest neighbors, should scale with the size of the data set, because otherwise you basically are not going to find any commonality at all for very small numbers of neighbors. So because the number of neighbors, in order to get a meaningful set of shared locations, you have to pay attention to that. So if you have 3,000 counties and you take 6 nearest neighbors in attribute space, you're not going to have very many commonalities. So, but for the Gary example, it works very well. So the result of this is a map like you see, where the darkest colors show how many common neighbors there are between the attribute nearest neighbors on the 6 variables and the geographic nearest neighbors. And there is one department that has 5 out of 6 in common, which is very rare. So the red lines are the neighbor graph that we have in GeoDa, but for the intersection between the 2 weights. So we do K nearest neighbors with geography, K nearest neighbors with variables, which is a new thing in GeoDa. And then we do the intersection, and that gives us how many are common, and we compute the p-values very quickly. You can also do this on other types of nearest neighbors. So just to illustrate what is going on in the transformation from high dimensions to smaller dimensions, multidimensional scaling is one approach that shows the data points in 2 or 3 dimensions, and supposedly in such a way that mimics their distances in high dimensions as close as possible. So now we can do the same thing. We can do the K nearest neighbors out of the 2-dimensional, multidimensional scaling scatter plot, and then do the intersection. And it doesn't give the same results. Why not? Because the dimensional scaling, depending on the method, does not necessarily reflect the nearest neighbors that well. In fact, the classic multidimensional scaling tends to work on having the larger distances reflected properly and not so much the local distances. And then a new method that we just implemented in GeoDa, TSNE, which is stochastic neighbor embedding, actually focuses on the close neighbors. So again, you can use these to visualize what is going on. And finally, the regional view is, so multidimensional scaling and principal components are dimension reduction techniques in variable space, as I call it. Regionalization is a dimension reduction in observation space. So the idea is that if observations are too similar, let's replace them by a larger entity. So that's the regionalization, and it comes in many flavors, redistricting, and all these. That's all basically the same idea. But again, we have the same tension. So if you run a standard clustering algorithm, say k-means, the resulting regions are not necessarily spatially contiguous. Now, some people would argue they don't have to be, and in some contexts, that's perfectly all right. But if you're interested in defining geographical regions, they should be connected or contiguous. So there is a tension going on there where you have to give up in terms of one criterion versus the other. So you either go all out and don't worry about the geography, or you go all out and force the geography. And then in GeoDa, you can also make a compromise between the two. So this is basically about visualizing the tension between attribute similarity and geographic similarity in clustering exercises. So the first one is, so if you realize that a multidimensional scaling scatter plot shows points that are close in multi-attribute space. So if you're familiar with k-means clustering and you have just points with their coordinates, if you do k-means on the coordinates of the points, you get very nice compact regions. It just minimizes the internal distances of the points. It's a kind of cheater way to do quick point clustering. You apply k-means to the coordinates. And you can do this on the coordinates in a multidimensional scaling scatter plot as well. But now the coordinates are not locations in geography, but they're locations in multi-attribute space. So you get nice compact regions in multi-attribute space, which is basically what k-means clustering is all about. So we can now visualize that, and I'll show you how you can trick GeoDa into actually doing this. Because right now, GeoDa doesn't have attribute mapping in a scatter plot, but it's in the works. But you can use the bubble chart to mimic that. So here you have, on the left, I guess it's on the left, right? Yeah, on the left, you have the clusters, the k-means clusters on the points in a two-dimensional, multidimensional scatter plot. So these are the 6 dimensions reduced to 2. Points that are close together in high dimensional space. And then on the right, you have the geographic reflection of that. And so one thing that you see is that for some of these clusters, they make a lot more geographical sense than others, right? And so then you can start exploring that, and actually in an interactive way, you can start moving departments in and out of different clusters and so on. So that's one way of looking at it. And then the other direction is doing spatially constrained clustering, like a scatter, which gives you the regions, and then see, how do these regions translate in your multidimensional scatter plot? In other words, how much do you have to give up in terms of attribute similarity to get your nice spatial regions? And so here we have the scatter regions, and for example, for the light blue one, things seem to be fairly connected. I have to figure out how to use a pointer on this thing, but I'm almost done. So, but then there's this blue one that's way off in the distance. And so you can start seeing what is going on here in terms of what are we giving up to get the spatial contiguity satisfied in terms of the similarity among the other variables. So this is nothing revolutionary, but it's just, forcing you to think about the tension between these two attributes in a kind of a more careful way, rather than just slapping down a clustering and running with the results.